Okay, today we'll discuss the key data processing and modeling steps for the liver disease classification dataset. The aim of this project to build a machine learning model based on the cirrhosis patient data to predict whether the patient will develop into advanced cirrhosis. The data comes from the real clinical experiment of Mayo Clinic, covering detailed records of the 424 patients, including biomarkers, pathological stages, and other characteristic variables of the patients. Cirrhosis is a serious disease, and the prediction model can help detect the high-risk patients early, assist the clinical decision-making, and optimize the resource allocation. The target variable of this dataset is stage, which is originally classified from 1 to 4 for the convenience of the modeling. It is recorded as a binary test. 1 indicates the advanced cirrhosis and 0 indicates other stages. The particularity of this test is reflected in the actual scenarios of the medical prediction and resource management. Data processing is the basis of the modeling and direct the fast performance and interpretability of the model. To address the challenges of missing values and outliers in the dataset, we implemented robust techniques. For instance, features such as collateral and copper with the significant missing values were handled through the imputation and substitution. Meanwhile, outliers was proceed using the logarithmic transformation and the Turkey rule, recognizing the imbalance of the target variable categories, positive simples accounting for only 24%, and this applied to smooth algorithm to oversimple the training data. Additionally, standardization was performed to scale the numerical variables, reducing the impact of the different dimensions on the model. The correlation heat map further highlighted the relationship between the variables, uh, prioritizing key features such as bilirubin and albumin. These systematic steps laid the groundwork to accurate modeling, building, and transition from data preparation. We moved to an equity crucial phase, selecting and validating the best model for our protective test. This project explored the variety of the models, including logistic regression, decision trees, and Pancreas tools. The compare performance logistic regression, our benchmark model, we chosen for its simplicity and interpretability in the medical field. Through its performance is limited in the capturing complex nonlinear relationships. On the other hand, decision trees exist. Decision trees exist and handling nonlinear data through their benching structures to streamline the compression and achieve optimal the performance. Python, a low code machine learning tool, enable automate the model selection and ultimately random forests emerged as the best performing model. Validation was conducted using the stratified T4 cross validation and research optimization, ensuring balanced distributions in training and test samples. With robust validation framework in place, we validate the model's effectiveness and delved deeper into their technical nations. So the evaluation focused on the metrics such as accuracy, recall, and F1 score, logistic regression, achieved the test accuracy of the 64%, effectively capturing linear relationships but struggling with nonlinear patterns. Decision trees demonstrates slightly higher accuracy at 64.2% and improved recall, benefiting from the smooth handling of the imbalanced data. PyCred, through the automated tools, fine-tuned a random forest model to achieve the highest F1 score among all the methods. From technical perspective, logistic regression faces a challenge with high bias, while decision trees, so prone to the high variance, benefit from cross-validation and balanced data. These insights underscore the importance of the selecting appropriate models and techniques to the problem. Aimed with these findings, we move to the analysis of the practical applications and the implications of our predictive model. Analyze revealed the bilirubin and albumin, and each were the most critical predictors of the liver cirrhosis progression. Lying with the clinical understanding, elevated bilirubin levels indicate the liver damage, while decreased albumin reflects the diminished liver function. These medically interpretable features enhance the model's credibility and its utility to the clinicians. And practical applications, the model can optimize the diagnostic workflows, prioritize the high-risk patients, and ensure efficient allocation to limit medical resource. Furthermore, it's automated in the implementation highlights to the potential of the machine learning in broader medical applications, opening avenues for the future innovations. Building on these achievements, we now reflect on the overall outcomes and further possibilities. In summary, the study constructed the efficient binary classification model through the data prep processing, model selection, and performance optimization, efficiently predicting the late-stage risk in the cirrhosis patients. This project highlights the practical value of the machine learning in the medical field and the systematic approach of the data science in addressing complex challenges. Further research to further expand the data set, refine the feature selection, and incorporate additional clinical variables to enhance the predictive power. By leveraging these achievements, this work can profoundly impact the medical resource management and patient care. That will be all. Thank you.